Right, so move on to example 6. We want to determine the Laplace transform of this function t squared times u of t minus 1. So very similar to example 5. The shift, you have to determine the shift, right? So c is equal to 1 in this case, and g of t is equal to t squared. So go back to this. I'm going to use this formula right here to find the Laplace transform of the functions. So here, c is equal to 1 and g of t is equal to t squared. Then the Laplace transform of t squared times u of t minus 1 is equal to e to the negative 1 times s times the Laplace transform of g of t plus 1. For g of t is equal to t squared, therefore g of t plus 1 is going to be, so e to the negative s times Laplace transform of t plus 1 altogether squared. Any questions on this? Good. Then before we apply the Laplace transform, we need to expand t plus 1 squared. So this gives me e to the negative s times Laplace transform of t squared plus 2t plus 1. So Laplace transform of the sum is the sum of Laplace transforms. So you have e to the negative s times Laplace transform of t squared plus 2 times Laplace transform of t plus Laplace transform of 1. So Laplace transform of 1, you got it, is 1 over s. Laplace transform of t, for the last two examples, you have seen that before already. It's going to be 1 over s squared. Now for Laplace transform of t squared, let me go back to Laplace transform table again. So Laplace transform of t squared, in this case, n is equal to 2, so you have 2 factorial over s to the power 2 plus 1, or 2 over s cubed. So Laplace transform of t squared is 2 over s cubed. This is equal to e to the negative s times 2 over s cubed plus 2 times Laplace transform of t, or 2 times 1 over s squared, plus Laplace transform of 1 is 1 over s, and that is the answer for the Laplace transform that you're looking for. Any questions? Okay, now we're going to move on to example 7. We have a piecewise defined function written in this form. So as you can see, of course you can use definitions of Laplace transform to find the Laplace transform of this piecewise defined functions, but for the sake of this functions and the topic that we are covering right now, we're going to rewrite this function in terms of unit step function and shifted unit step functions. Okay, so you start with sine of t, and then that's the first function in the interval between 0 and pi over 4. So first, we rewrite f of t in terms of shifted unit step functions. As follows. So you start with the first function f of t. So you have psi of t times u of t, which is basically sine of t. And for f2t, you have sine of t times u of t plus u of t minus pi over 4, right? Because you shift it to the right by pi over 4 units. Now, what is the coefficients? For the coefficient, you get the new functions, subtract the old functions. So sine of t plus cosine of t minus 4, subtract sine of t. So sine of t minus sine of t, you're only left with the coefficients of cosine of t minus pi over 4. Do you see that? Now, any questions on this? Then the function, one more time.
No, that's good.
Okay, so then the functions f of t is equal to sine of t plus cosine of t minus pi over 4 times u of t minus pi over 4. As I mentioned above, that you can write down u of t, or you can just don't have to write down u of t. So apply Laplace transform. Laplace transform of f of t is equal to Laplace transform of sine of t plus cosine of t minus pi over 4 times u of t minus pi over 4. Laplace transform of the sum is the sum of Laplace transform. So Laplace transform of psi of t plus Laplace transform of cosine of t minus pi over 4 times u of t minus pi over 4. So Laplace transform of psi of t is straightforward. You just need to go to Laplace transform table right here and look at number 24. So Laplace transform of psi of t is 1 over s squared plus 1 squared, or is equal to 1 over s squared plus 1. Now for Laplace transform of cosine of t minus pi over 4 times u of t minus pi over 4. So the shift here is pi over 4. So c is equal to pi over 4. A quick note here, c is equal to pi over 4. That is the shift. Then you go back to this formula or go to the Laplace transform table. Either way should work. So this is the functions that you're looking at right here. Right? So you have cosine of t minus pi over 4 times u of t minus pi over 4. So the Laplace transform is equal to e to the power negative cs times the Laplace transform of the functions. So you get this is plus e to the negative pi over 4s. Right, so c is equal to pi over 4 times the Laplace transform of the functions. Here, this is the function f. Right? So f in this case is going to be just cosine of t, because pi over 4 is the shift. Right? So just cosine of t. Then you go back to the Laplace transform table to look at the Laplace transform of cosine of t. So you look at this function number 20, equation number 25. So cosine of t, in this case, b is equal to 1. Laplace transform of cosine of t is s over s squared plus 1 squared. Or you get 1 over s squared plus 1 plus e to the negative pi over 4 s times s over s squared plus 1. Are we good with this? Any questions? Okay,
no.
Good. Now we're done with Laplace transform. We're going to move on to doing similar calculations, but for the inverse Laplace transform of some functions. Okay, so the inverse Laplace transform is, again, it's not straightforward. You have to do a little bit of work to see how you get the answer. Okay, so given a function in the frequency domain of the form 1 minus e to the negative 2s divided by s squared, you want to find the inverse Laplace transform of this function. So how can you do it? So this is the fractions. If you look at this problem directly in the Laplace transform table, there's no similar functions that you can find. So what you do is you separate this into two different fractions. That is, this is 1 over s squared minus e to the negative 2s over s squared. Okay. Then apply the inverse Laplace transform. Okay. Then the inverse Laplace transform is so you have y of t equal to, sorry, f of t. Right? So f of t is equal to the inverse Laplace transform of 1 over s squared minus negative 2 over s, sorry, e to the negative 2s over s squared. So inverse Laplace transform of a difference is difference of inverse Laplace transforms. So you have inverse Laplace transform of 1 over s squared minus inverse Laplace transform of e to the negative 2s times 1 over s squared. So I write like this is because it's convenient for me to do the work a little bit later. So when you look at the Laplace transform table, you can find the inverse Laplace transform of 1 over s squared. So 1 over s squared, go to Laplace transform table, look at this formula right here. So 1 over s squared indicate that n is equal to 1. So 1 factorial over s to the power 1 plus 1, so 1 over s squared. So n is equal to 1, so the inverse Laplace transform is t. So the inverse Laplace transform of this function is t. Now what about this problem? So you have e to the negative 2s, so the 2 there is going to be the shift, the delay, right? So the physical interpretations that I give you in lecture 14 when we have something like this is that you turn on the faucet, right? The water coming out at the rate of 1 over s squared after 2 seconds, right? So you delayed the rate to 2, like the minute 2 or something like that, or after 2 minutes or after 2 seconds. So the shift or the delay here is c equal to 2. Right. So e to the negative 2s time 1 over s squared. So this part right here is going to be a Laplace transform of some functions. Okay, how do I know that? Like, again, go back to the Laplace transform table here. So you have e to the negative 2s times a function, right? And that function is the Laplace transform of something. So that is inverse Laplace transform of e to the negative 2s times Laplace transform of something here. So 1 over s squared, as you can see, is Laplace transform of t. And this whole formula is going to give me, remember again, the delay here or the shift here is c equal to 2. So the inverse Laplace transform give me u of t minus 2 times f of t minus 2. Right. So f of t is t minus 2 is going to be t minus 2. So multiply with t minus 2 here. You okay with that? Any questions?
Explain that one more time.
Okay. Yeah. So you okay with the shift c is equal to 2, right?
Yes.
Okay. Now the formula for the Laplace transform of, let me write over here, of the functions f of t minus 2 times u, sorry, f of t minus c times u of t minus c. You okay with this? The Laplace transform of this is e to the negative cs times the Laplace transform of f of t. You okay with it, with this formula?
Yeah.
Okay. So what do you have? You have this part of the formula for this example, right? What are we looking for? We're looking for f of t minus c times u of t minus c. Sorry, c, not 2. So this is what you're looking for. Okay, and the formula is the inverse Laplace transform of e to the negative cs times Laplace transform of f of t. So we establish and we agree that the shift c is equal to 2. What we're looking for now is this part of the formula. What is the Laplace transform of f of t? So Laplace transform of f of t is 1 over s. Then what is f of t? So f of t is t. Okay. And therefore, you get c is equal to 2. F of t is equal to t. And with this information, you put it back to our formula right here. You get f of t is equal to t. Therefore, f of t minus c, in this case c is equal to 2, is t minus 2 times u of t minus 2. You okay with that?
So they're just using the table of the given function, and now we have a constant, now we know what the function t is, and substitute it back in.
Yes, yes. Okay. Any questions? Yeah. Okay, good. Now we need to graph this function, so it's hard to see how we can graph this function written in terms of the shifted unit step functions. Okay, so what you do is you turn this into a piecewise defined function. It's a lot easier to look at in terms of graphing. Okay, so let me get rid of this information. Or let me move this to the below here. Okay. Right, so let's rewrite this functions in terms of piecewise defined function. So you have t minus 2 multiplied with u of t minus 2. This is equal to 0 as t is less than 2, and is equal to 1 when t is greater than 2. Okay. And then you multiply t minus 2 in, right? So t minus 2 times 0 is 0. T minus 2 times 1 is t minus 2. So you get t minus 0, and this is t minus 2 times 1 is t minus 2 when t is greater than 2. And then combine this together. So t by itself indicate that the interval from negative infinity to positive infinity is t. Right? So that's why we can write like that. And then t minus 0 is t when t is less than 2. And then you have t minus t plus 2. T minus t plus 2 for t is greater than 2. T minus t plus 2 is just 2. So in terms of piecewise defined functions, this t minus u of t minus 2 times t minus 2 is written in this way. So t when t is less than 2 and the function is equal to 2 when t is greater than 2. So in the interval for t is less than 2, the function is t. And the function is equal to 2 when t is greater than 2. So this is the graph of the functions that we got here. You okay with that process?
Yeah.
Good? All right. Now I'm going to consider example 9. I have 10 more minutes. Example 9 and example 10. Let me do example 9 and see what happened. So let me minimize this a little bit. So inverse Laplace transform of 1 over s minus 4 times e to the negative 2s. In this case, e to the negative 2s give you the information about the shift. Right? So c is equal to 2 in this case. So here, c is equal to 2. Everyone agree with me on that, right? Any questions, any rejections on that? Good. So the inverse Laplace transform of, let's say, e to the negative 2s times 1 over s minus 4. So the procedure is very similar to the last example, right? So you already established that c is equal to 2. You understand the shift. Now what about 1 over s minus 4? Right? So that should be the Laplace transform of some functions. Right? So then you go back to the Laplace transform table and see if there is anything related to 1 over s minus 4. When you look at the Laplace transform table, you can see something here. You have the formula 15. You have 1 over s minus a, for a is equal to 4 in this case. Okay, so go back to the note. So 1 over s minus 4 give you the Laplace transform of e to the 4t. So this is inverse Laplace transform of e to the negative 2s times Laplace transform of e to the 4t. Okay. Now again, what you're looking for, what formula are you working with? So I'm going to copy what I have earlier here. So Laplace transform of f of t minus c times u of t minus c is equal to e to the negative cs times the Laplace transform of f of t. Given that c is equal to 2, right? You know that c is equal to 2, and f of t, in this case, from our analysis, f of t is e to the 4t. So when you apply this inverse Laplace transform, you're going to get f of t minus c, or e to the 4 times t minus 2 times u of t minus 2. So that is the inverse Laplace transform that you're looking for. Any questions on this? You follow? You understand where is e to the 4t coming from? Yes? And why we have...
Yeah.
Good. And why we have...
I think you'll connect more, probably with the homework.
Okay, yeah.
But yeah, I think I'm a little bit intimidated, but I think I'm
okay. So just one more time here. You okay with c equal to be 2? No questions on that, right?
No.
Alright. About 1 over s minus 4, you okay with the idea that 1 over s minus 4 is actually the Laplace transform of e to the 4t, yes?
Yeah.
Okay, so you establish that c is equal to 2 and f of t is equal to e to the 4t. So the job now is just to write down this part of the formula, or what you have here. Let me be careful here. Leave one more step. So if you find the inverse Laplace transform, this is inverse Laplace transform of e to the negative cs times Laplace transform of f of t. Given that you know the value of c, you know the value of f of t. Okay. So f of t is equal to e to the 4t. Therefore, f of t minus 2 is equal to e to the 4 times t minus 2. Okay. And that's why the answer here for the inverse Laplace transform is e to the 4 times t minus 2 times u of t minus 2. Good?
Yeah.
All right.
Are there other identities like that, or formulas, when we're going to solve piecewise functions, or is it mainly just this one?
There are all other, So for instance, so this is the 4 that you usually see in terms of step functions and periodic functions. Mainly that you're going to see. Okay.
Okay, so don't worry about the edge cases where they don't work.
There's when the case that's not going to work, you will see later in about 2 more lectures or something like that. When you find the inverse Laplace transform of when you find the inverse Laplace transform of this product, right? So you have inverse Laplace transform of the sum is the sum of inverse Laplace transform. But I didn't talk about inverse Laplace transform of a product, right? We have to follow a certain formula, for example, this formula. But there's a lot of cases where you have a product and you cannot use the Laplace transform table at all to find the inverse Laplace transform. When that is the case, you use something called convolution. That's just part of what we're going to cover next week, or tomorrow for that matter. That is where you have to do the convolution integral to find the inverse Laplace transform. Right? So there are certain function that's not going to work using the Laplace transform table, and there is a product in between 2 functions. When that is the case, you're going to use convolutions to tackle that issue. Okay. So let's move on to example 10. In example 10, you want to evaluate the inverse Laplace transform of the function s over s squared plus 9 times e to the negative pi s over 2. Here, again, similar to the last 2 examples, the first thing you need to identify is the shift. So here, you see that c is equal to pi over 2. Now next, we're going to rewrite the inverse Laplace transform a little bit so that it's in the form that we can recognize by using the formula. So inverse Laplace transform of e to the negative pi s over 2 times s over s squared plus 9. So let's go back to the Laplace transform table here. Let's take a look at this formula in the table. If we could be able to rewrite the functions that we got inside the inverse Laplace transform into the form of e to the negative c times s times the Laplace transform of a function's little f, then we can use this particular formula. So we have e to the negative c times s. Now for the function s over s squared plus 9, let's write that in terms of Laplace transform of a functions. Okay, so let me go back to here. You have e to the negative pi s over 2, you have the value of c. Now what about s over s squared plus 9? So s over s squared plus 9, let's go to Laplace transform table. So you have the formula s over s squared plus b squared, for b is equal to 3 in this case. So the Laplace transform of s over s squared plus 9 is cosine of 3t. So let's go back to the note here. So this expressions can be written as inverse Laplace transform of e to the negative pi s over 2 times Laplace transform of cosine of 3t. And then you can use the formula that we see earlier. So let me include the formula over here. So you want to find Laplace transform of f of t minus c times u of t minus c equal to e to the negative cs times Laplace transform of f of t. So here you have c to be equal to pi over 2, and f of t is equal to cosine of 3t. And then if you apply the inverse Laplace transform on both sides of this equations, you get the equations of the form f of t minus c times u of t minus c times the inverse Laplace transform of e to the negative cs times Laplace transform of f of t, given that c is equal to pi over 2 and f of t is equal to cosine of 3t. And therefore, the inverse Laplace transform that we're looking for will result in cosine of 3 times t minus pi over 2 times u of t minus pi over 2. So we just finished some examples related to unit step functions, shifted unit step functions, and window functions.